Hi everyone, good morning for those on the east side of the planet, but thank you so much for joining us on this webinar. I think we can get started. If you're new here, I'm Anya, I'm handling business development of K-Mine. And just a heads up before we jump in, don't forget please to check out our and follow our LinkedIn page. It's your go-to spot for all of our latest news and future streams. And thanks for being with us in our final stream of 2023. Awesome to see you all. And it's our special Christmas edition webinar. We've got someone as festive as me. Please welcome Vitaly. He's a mining engineer from K-Mine. Hi, Vitaly.
Hey, hello. Nice to see you.
I like your ugly sweater too.
Yeah, thanks my wife for that.
Great. So Vitaly will answer your questions in the end of the stream. So today our session is dedicated to mine planners, economists, business analytics, and C-level managers. We'll cover key mining planning aspects like optimization, design, scheduling, and plus financial analysts will learn how to assess a deposit's investment appeal alongside insights into financial analysis and economic indicators like IRR, NPV, EBITDA, margin, and others. But first, let me give you a short overview about our company, since we will show all the processes of planning based on our software. We have been around since 1994. Initially, we were based in Ukraine, but over time, we have grown to offices in Europe, Asia, and beyond. Now, we're also in the United States and Canada, and working through resellers in Chile, Brazil, Australia, South Africa, and other countries. Our large team includes developers, surveyors, geologists, mining engineers, and some of them also work as qualified persons for compliant reports, whether it's NI-43 reports or JORC reports. So our client list is pretty diverse. We're big on making things cost effective, so we work with everyone from small exploration teams and independent consultants to big name corporations. And the software itself is end-to-end, so it's like a Swiss Army knife for the mining world. We aim to cover the entire mining journey from the start of exploration right through to the production. It's all packed with 12 flexible models that can handle open pit or underground sites. And the best part is that you can mix and match these models to fit exactly your workflow. So you can use one model or all 12. It's super easy because everything runs in one interface. And all these models are great for things like processing geological and surveying information, or creating optimized short or long-term mine plans with the possibility of visualization of these processes in real time. We also all about tailoring our approach to unique mining project, whether it's exploration, development, or production. We've got your back covered with extra support through our consulting services. So we don't give you software and call it a day. As a separate service, our engineers also are ready to dive into creating 3D models, strategizing plans, or figuring out resource and reserves estimates. Our software didn't just come from theory, it's born from real challenges and projects we faced in our consultancy work, and that's how we knew what to tweak and add to make things faster and better for those that actually work in consulting business. So now our software can do things like evaluate projects, create digital twins, and plan out the entire life of mine and more. So if this list of services piqued your interest, if you want to find out more, please don't hesitate to reach out to us in the comment section. So here's how we are going to shape our meeting today. First, we'll dive into optimization, starting right from the basics. Next, we'll sketch out the final pit design and walk through the timeline all the way till the end of the project. Then we'll delve into the financial aspects, and we've got some short videos lined up to give you a clear idea how our planning models work. And finally, we'll explore key economic indicators that matter in project evaluation and how to track them efficiently and effectively, with a special focus on managing rock mass in stockpiles and equipment calculations. So today we will show all of our examples based on the zircon deposit. I want to give you some quick facts about this mineral. Zircon is a mineral you often find in acidic and alkaline igneous rocks, pegmatites, nepheline, cyanides, and even other like certain places. Usually it hangs out near other minerals like apatite, titanite, and magnetite. It's pretty widespread with significant deposits in places like southern Norway, Brazil, United States, Sri Lanka, Madagascar, and Ukraine. Ukraine actually has the third largest deposit in the world. This mineral is a big deal for producing zirconium oxide and hafnium. It's not just about industry though. Zircon also very popular in jewelry, making tough materials for high heat situations, like in glass melting or steel melting furnaces, and even used in foundries. Plus, zircon plays a key role in dating rocks with the lead method. And zirconium powders actually have this unique trait. They burn super fast in the air at the super low temperatures, around 250, relatively low temperatures, around 250 degrees Celsius. And they can get as hot as 4,650 degrees Celsius. That makes them a go-to choice in pyrotechnics like fireworks, chemical light sources. But that's not all. They also used in the military stuff. Think rocket fuel, artillery, ammo, tracer bullets, blasting caps, and that's all because they have a low flash point and burn quickly. So you can see on the slide a few examples of what it looks like. In the picture with the ruler, you see crystalline zirconium obtained using a gas transport reaction. On the other picture, you see these two zirconium bars. They're pretty special, both of them crystalline, and have a purity of 99.97%, but each has unique surface texture. They were made using a technique called the Van Arkelden-Boyer method or the iodine method. And then for a bit of comparison, we also got this tiny cube. Next to them, it's just a 1 cubic centimeter, but it's made of high purity zirconium-2 at 99.95%. All right, let's get into the heart of today's discussion. First, let's talk about strategy. The big goal of strategic planning is figuring out the best direction for company growth, understanding what you should do, how you should do it, and when, all to make sure you are profitable and as profitable as you can be. Usually we'll go with the option that brings in the most profit in the least amount of time. Now, diving into the specifics, we'll start with some key initial data. This includes target productivity for our ore plant, the capital expenditure, and the various costs tied to producing concentrate. We'll focus on a few essential indicators like the ones that you see on the screen. They are really key on sizing up the project. And on the slide, you see the main parameters we are working with and what we expect these crucial indicators to look like. So let's start with searching for the optimal contour along the way, and I'll showcase the main features of our pit optimizer model. Just a heads up, all the data we are using in this stream have been crafted by our team specifically for this demo. And remember, it doesn't represent any actual deposit or real-time economic indicators. So as a search range, we will select the final product price adjustment factors between 0.1 and 1.2 with 5% increments. The final product's price is set as $2,200 per ton of concentrate. Processing cost is fixed at $20 per ton of processed ore. Regarding the cutoff grade, there are multiple approaches. Either outline the ore body based on specific quality in the block model and ignore this field in the settings, or define a necessary indicator to incorporate the data as anticipated. In determining the conversion ratio from the ore that is raw to final product, we'll establish variable ranges. A high quality results in greater yield, and it's fine to repeat the quality below the cutoff grade such that it just will be excluded from the calculations. So we set mining operation cost at $2 per ton for both ore and overburden, with losses and dilution at 2%. Rock transportation costs are also $2 per ton. For NPV calculations, we use an 8% discount rate, assuming ore productivity of 1 million tons annually. We also focus on marginal profitability indicator of 20% as a key metric for optimal final contour selection. Then we examine outcomes generated by the automated pseudo-flow block evaluation method, which employs the Large-Grossman algorithm. Earlier results at coefficient 0.2 suggest high project profitability, and we can visualize block sets progressively as the prices rise, observing the pit expansion trades. We've included buttons for easier navigation through these block sets. So to visualize this, we use graphs accessible in multiple modes for both tables and graphs. These various graphical representations in different modes provide essential information for you to make a decision, and then it's up to engineer. It all depends on his experience and abilities. So check it out on option highlighted in yellow, signifying a 20% marginal profitability in incremental mode. And this option serves as a project evaluation metric that can be adjusted in settings to desired values. It assists in determining the optimal final contour. Now we consider accepting a contour with 20% marginal profitability. Given other favorite indicators like life of mine, NPV, and overall profitability. Let's review the block evaluation results for this contour. So the ore weight around 10 million tons, overburden weights at 45 million tons, a reasonable stripping ratio, and an NPV of $700 million in optimization, and that's excluding capex and considering high productivity. The NPV recalculated is likely to be half. The quality of rocks in the contour ranges from a lower limit of 0.2 to an average of 0.31. To determine indicators that significantly affect the project, we need to perform a sensitivity analysis to identify key project influencers using a plugin that separates general and unique indicators focused on NPV or profit. Our analysis makes it clear that the recovery factor is a key player here. It's important for us to think about how we can have a positive impact on this aspect. Also, raising the lower limit of the cutoff grade is very significant. This will lead to an inevitable loss of profitability, and these evaluations provide more comprehensive understanding of the project. Next, in order to build a long-term calendar plan, it is necessary to divide field into pushbacks. So we employed a manual construction with guide polylines for this process. 3 mineable pushbacks were created, each designed to illustrate pit expansion as the price coefficient increases. This approach aims to enhance the theoretical NPV indicators for each pushback. Also, we wanted to show you a relatively new feature of our plugin. It's called estimation of specified boundary. To use this feature, a project needs to be pre-completed. Essentially, we're getting a bit ahead of ourselves to ensure we won't tear our optimization model into pieces. The subsequent step involves exploring how to construct the same final contour within a specialized model. Now, we'll examine the outcome. This feature enables us to assess an externally defined contour based on the economic parameters sets in given scenario. So let's check out the results. It looks like we managed to get almost all of the ore out, though we did end up with a bit more overburden than expected. This is inevitable since the optimization loop doesn't take roads into account. And utilizing this method, you can assess various contours such as a specific project or compare outcomes from multiple optimization efforts. Also, in the pit optimizer model, there is this ability to create a calendar plan based on specific search parameters. It's really useful for getting big picture view of the project direction, especially in terms of the economic aspects. When you crunch the numbers, it will give you 3 scenarios. Among these, the maximum profit option is customizable, providing flexibility for fine tuning. The other two are more like a ballpark figures, just to give you a sense of where the things might land. These initial results also from the planner, like good starting point, but we're going to dive in deeper, come up with a plan that is more detailed and easier to manage. So after we figure out the optimal contour in our planning process, the next logical step is to create a design that is of a final pit contour and all of its pushbacks. We're going to show how swiftly we can put together a plan for the design of a pit, and we'll be using our zirconium deposit as an example, applying a specialized section of the design model known as dynamic design. Dynamic design is a key component of our design model. It's incredibly helpful for quickly and efficiently shaping the final outlines of pits and other major pit elements. Usually, creating this manually can take ages. So when you start working with the plugin, the first step is to get some guiding lines. You do this by using the command to create ISO objects. In the settings, we'll specify elevation marks, and then the plugin will generate ISO lines all along the frame height. It's a real time saver. So let's remove the unnecessary, and what I mean by the unnecessary is something that cannot be worked out for reasons of geometry. After that, we can smooth out the line, organize the points, maybe even cut down their number, or we can use the lines we've got to build our own, making sure we keep the geometry of pit shell intact. Then it's time to bring up the dynamic design from form itself and start setting up the parameters for our list of horizons. Next, we match each line to its respective horizon and make initial build, leaving out the roads for now. This will give us a pit that will later expand by adding roads. So to do this, we set up the road parameters and mark the first point where the road would start. The cool part is that you can move this starting point around and the whole project updates instantly with new parameters. That's the beauty of this plugin. It's all about dynamic design and where changes happen in real time. So if we need to, we can easily add a switchback to the road by just changing its direction at a specific spot. It's possible to add as many roads as you want, but it's important to make sure they all work together. That's why we have tools that let you stop a road at a certain point, add a switchback, and even put in a flat section of a road between ramps. All of these changes are clearly marked. If you highlight a part of the road in the table, it will also be highlighted in the Kmine workspace. This kind of indicative sampling is a real-time saver during the construction. Plus, we can put horizontal segments where two ramps meet and widen switchbacks to make sure there is enough turning radius for the heavy-duty dump trucks. So let's add a couple more limiters and change the parameters of the ledges to align our project as closely as possible with the desired shell. And then we'll compare what we've got with what we're aiming for. Once we're happy with how everything looks, we'll just move on to drawing up the actual physical lines and make adjustments to any areas that need to be a fine tuning. After that, we'll all set to construct a wireframe and calculate volumes and so on. So let's take a quick example to see how we can quickly build dumps. We'll start by using a polyline, just a polyline to mark out the construction area, and then we'll smooth it out using the inscribe object command. Next, we'll tweak the damp settings on the list of levels, things like enlarging down the berms, adjusting slope angles, and increasing tier heights. After that, we'll add a road, and its parameters will be a bit different from those in the pit to ensure easy navigation through the dump tiers. We'll widen the switchback and build a wireframe. So just in a few minutes, we can shape the final contours of the pit and the dumps. And if we were to do it manually, layer by layer, it will take just a whole day or maybe even longer. But with this tool, we can run just through various options and pick the best one without any fuss. And as you saw earlier, we already estimated and reviewed the results of comparison with the original shell. So let's move to the scheduling process. We add to the project the mining areas that we formed at the stage of creating the optimization project and add the conditions for the mining. Using Solution Finder, we set target search parameters for each interval and determine the sequence of rock excavation. When we activate the chosen interval, the block corresponding to the notch within this range will be visually represented in the workspace. So wherever we see a table, we can build a diagram. So it's a lot easier to understand what's going on. They're really flexible. You can tweak them as needed. Looking at our plans, it seems like we managed to keep the digging pretty even, no big ups and downs, which is great. We're keeping the amount of ore we dig up as steady as we can. Also, in the beginning, there is a need to open up the deposit, and in the end, the volumes of waste are minimal. This is what it's called quarry attenuation period. Moving forward, we can incorporate these metrics into our financial analysis and further refine our plan, this time including excavation machinery. We'll introduce excavators into our scheme, specifying their efficiency for different rock types and the order in which mining areas will be tackled. Next, we'll designate specific sites for depositing both overburden and extracted minerals. It's also crucial to organize key activities for the processing plant and set up the transport logistics. So in our transportation plan, we'll ensure that ore of lower quality is routed to one storage facility, while the higher quality ore is directed to a separate location. So from our calculation, we'll get a detailed data for each block involved in creating the mining plan, and we can organize this information into a table, categorizing it by intervals and unloading points, also the total for each category. The visualization tab also allows you to visually demonstrate the work sites on the specific day of the plan. It includes a feature for navigating through calendar dates. This is particularly useful as it allows us to pinpoint exactly where mining activities will be on any given day, and provided we stick to the plan. So we can analyze the outcomes over different periods, which, as we've seen, can be approached in two distinct ways. Alternatively, we can merge these methods just by initially determine the sequence of operations using the solution finder, and then just reconfigure the sections into the results by intervals and arrange the equipment. So now let's begin examining the outcomes of the mining the rock mass. We'll delve into the results of our economic analysis, which is based on the data we've gathered. All right, so let's walk through each part of our model line by line and just discuss it. Based on what we calculated in the mining model using our starting figures, we're looking at a life of mine stretching up to 2041. The data concerning the volume of overburden and ore extracted from the pit were obtained during the excavation sequence planned in the scheduler model. These figures are manually input in our model, and all other indicators have been calculated. In our model, we categorize the ore extracted from the pit in two streams, one directed to the warehouse and another to the factory. The ore with the lowest concentration of valuable components is sent to the warehouse and in quantities exceeding what's needed for concentrate production. And this strategy is aimed to enhancing overall yield by improving the average quality of the mined ore. Later on, when there is a shortfall of ore from the pit, we'll compensate for it with the stock from the warehouse. However, a downside of this approach is the need of re-excavation the rock mass, which incurs additional costs. Additionally, There might be taxes associated with the storage of mineral resources, and all these factors need to be considered for possibly in various scenarios for comprehensive comparison. So let's break down how we calculate the stockpile balance. It's pretty straightforward. We take the balance from the last period, add in the ore we brought in from the pit, and then subtract what we've sent from the warehouse to the factory. Our plan is to gradually increase the balance in the warehouse, especially towards the later stages. Ideally, we want to keep this balance as minimal as possible, but having some reserve is key for boosting the average quality of the ore, which in turn increases our yield. Initially, we won't be putting anything into our warehouse, and this will start once we hit target ore productivity levels. In our approach, the stripping ratio is determined by dividing the amount of overburden by the amount of ore, essentially a tons to tons comparison. During the initial phases, we are focusing on increasing the overburden to access the ore, a process known as ore body opening. And our average stripping ratio stands at 4.18, which is relatively low. This is a positive indicator for our operations. By considering the needed concentrate volume and the average zircon content in the ore, we can estimate the target quantity of the ore required, and throughout the testing phase, we'll be closely tracking any variations from this benchmark. The recovery metric also is based on simple principle. The richer the ore, the higher the recovery rate. As for the concentrate amount, it's calculated by multiplying the quantity of the ore by the recovery rate. We then determine the revenue from the concentrate by multiplying its quantity with the selling price. Here, the price used is higher than what we assumed during the optimization, because in that scenario, we had adjusted the price downward to account for fixed cost associated with the concentrate. Next up, we'll tackle the calculation of operating expenses, or OPEX. This include mining cost, processing cost, general and administrative, loading cost for concentrate, and transporting charge. Each of these costs is calculated by multiplying the respective tonnage of ore or concentrate by the current rate per ton. Specifically, mining and processing costs are calculated per ton of ore, while the general administrative loading cost and transporting costs are based on per ton of concentrate. The government indicator encompasses a range of taxes calculated in line with the legislative standards of the country where the production or sales are taking place. Operating income is determined by subtracting the total costs, which include operating expenses and royalties, from the revenue generated from the concentrate sales. Additionally, where applicable, we calculate the cumulative sum of this indicator over the entire development period. For the capital expenditure section, we considering that our deposits and conditions are hypothetical, we've made assumptions based on our past experience. The only concrete figure we've calculated is the cost of storage, as it's a frequent occurrence in projects involving long-term storage, and the other aspects of the capex have been estimated based on our collective experience in similar scenarios. So next, we'll work on calculating depreciation. For this, we need the annual production data, which we can conveniently copy from the previous calculations. The cumulative production till the end indicator, as the name suggests, represents the total amount of concentrate produced from the current period until the end of development. The starting balance is the balance at the beginning of the period, essentially the end of the previous one. The additions line will reflect any additional capital expenditures, costs, and depreciation itself is calculated using the formula starting balance plus additions divided by cumulative production till the end, and then multiplied by the production for the period. And this method is just one way to calculate depreciation. And finally, the ending balance is determined by taking the sum of the starting balance and additions and then subtracting depreciation. So now let's calculate net income. We'll start by taking the operating income and duplicating it under the name of EBITDA. It's basically earning before interest, taxes, depreciation, and amortization, or EBITDA. Some people call it EBITDA. In this case, EBITDA is effectively the same as our operating income. Next, we'll replicate the depreciation figure, and we then compute the net income before tax by subtracting depreciation from EBITDA. We also incorporate income tax into our calculations by applying the relevant tax rate to EBITDA. This enables us to calculate net income, which is figured out by subtracting both depreciation and income tax from EBITDA. Next up, we'll determine the free cash flow before taxes. This is done by subtracting total capex from operating income. And following this, we'll calculate the pre-tax NPV. And all we just need to do is to apply the correct formula in Excel. Excel, in this case, doing a great job. They have like a lot of formulas like that. And we can conveniently use it as we need. Moving on, we'll compute our cash flow after taxes. This is calculated by taking EBITDA and then subtracting total capex and income tax. Naturally, we also calculate the NPV after taxes. We find that this figure stands at $312 million, and this result indicates that we successfully met our initial target as our net NPV was projected to exceed $300 million. Now, while it's not compulsory, but calculating the marginality per ton of the final product is extremely insightful for assessing overall profitability. For this, we first identify the costs associated with producing 1 ton of concentrate, considering the average stripping ratio. We sum these costs and then subtract them from the price of the final product. This gives us a figure of 1773, which translates to a 79% margin, a very high number, suggesting that the project could be highly profitable. These preliminary evaluations can be adapted to various scenarios, allowing us to assess the project from different angles. So moving on, we'll calculate internal rate of return, or IRR. This metric is commonly used to gauge the appeal of external investments, and conveniently Excel has a specific formula for this. And let's scratch out the numbers and see the result appears quite promising. And lastly, we'll look at the discounted payback period. This is calculated based on the total number of months the company operates at a loss, factoring it in discounting. The formula here is a bit more complex, but it's actually pretty logical and straightforward. If the accumulated discount cash flow after tax is less than 0, it implies that the year didn't break even, which equates to 12 months. If that's not the case, we look at whether the accumulated discounted cash flow after tax for the next period is less than 0. If it is, this means costs weren't recouped and resulting in another 12 months. Otherwise, we divide the negative accumulated discounted cash flow after tax from the previous period by the current period's discounted cash flow after tax and multiplied it by 12. Following this calculation, we find that starting from 2029, the project begins to yield a net present profit. So now let's delve into more detailed analysis of the production metrics for each period. We'll walk through them together. The chart we're looking at show the key figures for the extraction from the pit and concentrate production, which are usually our primary objective. So what is an engineer aiming for when setting these plant's volumes? The goal is to ensure consistent and even flow of ore to the plant. The specific methods for achieving this depend on the expertise of the engineer. In our scenario, the ore volumes sent to the factory align with our requirements, meaning that we can produce the necessary amount of concentrate in each period, And by the 6th period, we achieve our planned productivity, which we maintain up to and including the 17th period. Now, turning to the graph below, it illustrates the planned versus the actual profit figures for each period. And the overarching conclusion we can draw in this is that in almost all periods, the cash flow is likely to exceed our projections, probably because of the average ore content was higher than we initially anticipated. So the next chart, let's just switch here, presents the material flow from the pit, highlighting the average quality of the useful component. The key takeaway here is the stability of the volumes, meaning that there are no significant fluctuations. This applies to both overburden and mineral deposits. While there are some variations in quality metrics, it generally stays consistent around 0.32%. Initially, the overburden volumes are a bit higher, but they stabilize at around 2.8 million tons. As for the ore, it levels out at about 660,000 tons, which, as we observed earlier from the data, is sufficient for our needs. So next, let's discuss the process of calculating and selecting excavators and other equipment with a primary focus on the excavators. One approach is to start by selecting a range of excavators, each with unique features suitable for the required rock mass removal from the pit. We input these specific parameters into our calculation model to identify the best fit. Sometimes the strategy is reversed, especially when the goal is to expedite the pit development and increase production. In such cases, more productive excavators and dump trucks are needed, and depending on what the limiting factor or bottleneck is. So we've chosen 3 models with smaller buckets, and as we don't really need high output here, the key for us is working efficiently. To figure out the load rate, we simply divide the volume of the bucket by how long each cycle takes. Then we get the hourly direct productivity, and we multiply this load rate by 3,600. That's the number of seconds in an hour. After that, we multiply the direct productivity by the loosened density to get our calculated load rate. For effective utilization, we look at 2 things, availability and utilization rates. We multiply this together to see how effectively we can use our equipment during a shift. To work out the effective working time in a shift, we multiply the length of the shift by this effective utilization rate. Then, taking the direct productivity and multiplying it by this effective work time, that gives us our productivity for this shift. Finally, we calculate how much ore and overburden we can handle and multiply our shift productivity by the density of each material. And to get a yearly perspective, we scale this up and based on the number of shifts and days in a year. For dump trucks, we aimed for efficient operation. So the key was ensuring that loading a dump truck requires no more than 5 bucket loads of rock mass for optimal efficiency. Also, we compared 3 different dump trucks with varying body capacities. Depending on the capacity, different numbers of trucks are required to handle the necessary volume of rock mass. The selection of other equipment followed the principle no less than, with an additional 10% added to our calculated needs, rounded up to the nearest whole number. This results in 4 excavators with 1.5 cubic meters buckets. The number of trucks varies depending on the chosen truck model. And let's briefly touch on how the haulage distance changes as we move forward with the mining. We're seeing the gradual increase overall. Nothing too drastic though. There is like a notable peak early on. We might be able to smooth it out with a bit more detailed planning. Also, the chart plots the ton kilometers across different stages of development. This figure basically reflects 2 key things: the volume of rock mass we're moving and how far we're transporting it. So talking about our stockpile balance strategy, we decided to keep stockpiling to a minimum and only store a low-grade ore. This approach helps us to boost the average grade of the ore over the course of the development. Interestingly, the old stockpiled ore was used in just one period, which is the final one. Up until that point, the ore was just simply accumulating, reaching out around 230,000 tons. By ensuring consistent extraction of ore from the pit, we avoid having to transport the necessary rock to stockpile, which lets us effectively manage its balance. Overall, there are various strategies one can adopt here. For example, using all extracted ore in the mining, or distributing ore across multiple stockpiles for mixing, or blending to optimize results. The choice really depends on the specific needs of processing plant and overall development conditions. Ideally, you'd want to minimize sending ore to the warehouse, and as it involves re-excavation and potential degradation of ore properties if it's stored for too long. All right, so let's talk more about some other ways we might calculate our economic model. We've already seen one approach today, focusing on how assess the economical field development, but in practice, you often have to consider a bunch of different scenarios. For example, one thing we can think about is whether it's better to hire contractors or for the mining work, or buy our own equipment and handle it ourselves. Another possibility is ramping up the capacity of our factory, which could let us increase how much finished product we're putting out. We might also look into making some extra investments to bring down our mining and processing costs. Also, it's a good idea to compare the economics of working with different mining sizes and contours. Each option has its own set of economic details that we need to crunch. And then there is also a question of how fast we want the pit to operate. Generally, the quicker we work, the more we stand to earn. And lastly, we should consider the financial implications of using various combination of equipment and systems. Each combo could impact our bottom line in a different way. All right, so let's just bring back our festive Vitaly to the conversation and see if we have any questions here. So one of the question is, in the optimization model, you have the option to input all capital costs. The question is, should we handle this in the optimization model, or would it be better to do so in the economic model?
Okay, so let me think. Oh, I can think better. Okay, so I can divide this question by two different parts. So in the first part, and all of these parts are depend on what we would like to obtain as a result. So if you would like just compare a couple of results and choose the road which we would like to choose and proceed our planning process and so on, we can bring all our capex and put it into our optimizing scenario, and then just compare the results. For example, NPV, profits, and so on. But in case if you would like to compare and understand, like to obtain the deep understanding of how its indicators are work together. So in this case, we have to put into our module only capex that make influence into our scenario. So like, for example, to replace some factory, what capex should be, and we should place some polyline and bring this capex for it. So this is my answer.
And which of the economic indicators should be emphasized?
Okay, so I think that all investors will be interested in like the main question, when finally the investments will bring the profits. So to answer this question, we have the specific indicators: discounted payback period. Of course, all investors will be interested in total amount of the like profits, or discounted profits. So in this question could answer the NPV, so net present value. And I think if I would investor, I will be interested actually in all of the indicators, but like the third one, the key indicator, it will be like life of mine, because it tells us about how long I will be able to obtain like profits.
And is there a way to improve economic indicators through mining operations?
Sure. I'm like a miner. I can say that it is very important to try to obtain the much more profits in the first periods, because then rather we will go from our nearest period, then more our profits will be like uh, 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 beaten by discount. So it means like then faster we will get more profits, that higher will be our NPV value.
Got it. And I will have another question here. Do you consider a reclamation for the NPV calculation in this model?
Yeah, of course. Unfortunately, it was in the end of the table. The reclamation was in the last couple of years, I think 3 years. So the
Mhm.
one kind of reclamation, it's when we just bring out all our equipment, and this area will fill the water, and this some kind of like
Well, I think the question is just like if we take it into the
ah,
account when we calculate NPV. So the answer
yeah,
is
we
yes.
bring it. Yep.
Okay. Well, I think that's it from questions from the audience. Everything else we answered within the chat. Thank you so much, Vitaly. Thank you so much for all of you who joined us today. Thank you for 2023. Happy holidays, and we'll see you in 2024. Bye.
Okay, Merry Christmas. Bye.